Hello and welcome to the YouTube channel D Creations Resources. We are looking at different aspects of spectroscopy. Today let us talk about UV visible spectroscopy, especially its instrumentation. UV visible spectroscopy is basically a short form for ultraviolet visible spectrophotometry, and as it suggests, it deals with interaction of ultraviolet light as well as visible light from the electromagnetic spectrum with the material or the sample that is given. And this technique is used for measuring the absorption of ultraviolet and visible light by the sample or whatever is the chemical substance that has been used. Now, the principle, of course, is the fact that when this UV visible light will pass through a substance, certain wavelengths will be absorbed while others will be transmitted or reflected, and the amount of light absorbed at different wavelengths can provide valuable information about the concentration, about molecular structure, etc. And we can also, depending on what kind of a sample it is, we can also calculate some more parameters, for example band gap of a semiconducting material, etc. Now, of course, the principle is based on the electronic transitions of molecules. So when UV or visible light is absorbed by the molecule, the electrons within the molecule will be excited from a lower energy level, that is ground state, to a higher energy level, which is excited state. And the energy required for this transition corresponds to the difference between the two energy levels. And it is, of course, dependent on the molecular structure. Now, usually the wavelength regime for UV region is around 190 to 400 nanometer, and for visible region it's around 400 to 800 nanometer. Now, Beer-Lambert's law is central when you study UV visible spectrophotometry, which says that the amount of light absorbed A is given as product of three terms. E is the molar absorptivity or extinction coefficient, C is the concentration of the solution, and L is the path length of the cuvette. So A is equal to epsilon CL. And of course, here usually the unit for molar absorptivity or extinction coefficient is liter per mole per centimeter, or liter mole inverse centimeter inverse. For concentration, of course, it is mole per liter, and for path length it's going to be centimeter. Now, if you think of the instrumentation of this particular spectrophotometer, well, of course, there is going to be a light source, and then there is going to be a collimator followed by a monochromator. So there will be selection of wavelengths, and then you have your sample through which this light is going to pass, and finally you will have a detector. Now, in case of the light source, now we need two sources, one for ultraviolet light and the other one for visible radiation. Usually deuterium lamps are used as a source for ultraviolet light, and it's usually a gas filled tube. As you must be aware that deuterium is a heavy isotope of hydrogen. It is usually denoted as 2H, and it is one of the two stable isotopes of hydrogen. First, of course, is 1H, which is also known as protium. And deuterium nucleus contains one proton and one neutron, whereas protium has no neutrons. That is the basic difference between the two. And of course, deuterium also at the atom of deuterium contains two electrons. It's deuterium, the word comes from a Greek word called deuteros, which basically means second. So you will have a lamp which is filled with this deuterium gas, and inside this lamp there are going to be two electrodes, cathode and anode. So when an electric current will be applied, the gas inside the tube or the lamp is going to be ionized, and that is going to cause emission of light because electrons return to their lower energy states. and this is going to generate a continuous spectrum of ultraviolet light. So this stable and continuous emission in the ultraviolet range makes deuterium an important source for UV light in spectrophotometry. Now we also need visible light. So what do we use for that? Usually a tungsten halogen lamp is used, and as the name suggests, the lamp consists of a tungsten filament that heats up when an electrical current passes through it, and it's going to be filled with a small amount of halogen gas. It could be iodine or bromine. Now the range required, of course, is from 400 to around 750 nanometer, and the reason why halogen gas is also used here is because it extends the life of the filament. So when tungsten evaporates because of high heat, the halogen gas will react with it, and it will redeposit tungsten back into the onto the filament. So due to this, the darkening of the glass is also prevented, and brightness is maintained over a longer period. Now there is another option for light source, and that option is xenon lamps. So these can cover both UV and visible region, but of course they are very costly. So they may not be used where one needs an economical source. Now, if so many wavelengths are going to be, or a range of wavelengths are going to be emitted, you need to have isolation of a specific wavelength of light from the light source. So, a monochromator is used for that. So, you will have an entrance slit which will control the amount of light entering the monochromator. Then there will be a dispersing element. It could be a prism or a diffraction grating which is going to separate the light into individual wavelengths. And then there will be an exit slit. So this will ensure that only the desired wavelength is transmitted to the sample. Now naturally, the narrower a slit is, it is going to result in a better resolution, but there will be lower light intensity. Next, of course, is the sample holder. Now, if the sample is in solution form, a cuvette is used, and it is made up of quartz because you also need UV light to pass through. If one is checking only for visible light, you can also use a glass cuvette. And the path length of cuvette is usually 1 centimeter, or there could be, in fact, for very low quantity, there could be other kinds of cuvettes also, but that determines the path length. Now, I also want to mention here that the sample can also be in the form of a thin film. For example, a semiconducting material like xerano is usually subjected to UV visible spectrophotometry, where the sample is made in the form of a thin film. Now, after this, the next block is of detector. So the detector is going to measure the intensity of the transmitted light, and it is going to convert it into an electrical signal for analysis. So typical detectors that can be used are photomultiplier tube, that is PMT, or photodiodes, or sometimes even photovoltaic cells. Usually photodiodes are used in diode array detectors for rapid analysis across multiple wavelengths, and photomultiplier tube is a sensitive detector, so it can also be used for low intensity light. And photovoltaic cells are rarely used, only in very simple or less sensitive devices. We'll talk about PMT in detail, but before that, let me just mention that photodiode, of course, is a semiconductor device, and it's going to convert light into electrical current. And the principle it would use for that is the photoelectric effect, where photons, which are the particles associated with light, hit the diode, and that generates electron hole pairs. So there is a flow of electric current when you apply voltage. Gallium arsenide, that is GaAs, or indium gallium arsenide, that is InGaAs, also are materials apart from silicon which can be used for creating or making a photodiode. Talk about PMT, a photomultiplier tube. It contains a photocathode, diodes, and anode. So these are the three important parts. So the photocathode is of course at the front, and it is going to convert the incoming photon into electrons. The principle again is photoelectric effect. Then comes an important role of diodes. So after the electrons are emitted from the photocathode, they are accelerated and multiplied using a series of diodes. So each diode will be kept at a progressively higher voltage. So when electron hits a diode, it is going to release multiple secondary electrons, and this process will go on. So the signal gets amplified. And then of course you need an anode at the end of the PMT, which is going to collect these multiple electrons and create an electrical current which is going to be proportional to the intensity of the light which has been detected. So you can use PMT for range right from UV covering visible and also near infrared. So in many times in spectrophotometers, it's UV vis NIR. So UV visible and infrared, near infrared to be more specific. And PMT is highly sensitive. It has fast response time, and also it produces minimal electronic noise. So that goes for higher precision in the measurement. So it is preferred. And then finally, of course, you need a display system which will show the absorbance or transmittance values at different wavelengths. So usually if you plot it, it is going to be intensity versus wavelength, where the wavelength can be expressed in nanometer. So this is broadly the instrumentation of a UV visible spectrophotometer. Let's talk about some other aspects in upcoming episodes. Thank you.